These are the 3.3 notes, and we are looking at quadratic functions. So this is all review, like very heavy review. You learned all of this in Algebra 2 last year, but we're still going over it. It's good for us just to touch on it, look at quadratics again, and understand everything going on. And once we do this with quadratics, we'll start looking at polynomials. Polynomials and quadratics are very similar. Quadratics are a type of polynomial, to be honest, so they're not very similar. They're basically the exact same. Quadratics can just be broken down to be a little bit simpler. Since it only goes to the second power, we've got a lot of information that can help us. So, standard form of a quadratic function is f of x is equal to ax squared plus bx plus c, where a, b, and c are all real numbers and a cannot be equal to 0. If a is equal to 0, then you're looking at a linear equation. So anytime that you have x squared, once you have x squared as your base, you're looking at a quadratic function. We already learned that based off our parent functions. But this is standard form. Obviously, our quadratics, we're not always working with just an x squared. We can move from there. Quadratics opening up versus down. So if the a value is positive, the parabola opens up, and we call that concave up. So it looks like this, concave up. We're saying that the open part is facing up. If the a value is negative, the parabola opens down or is concave down. So the open part of that parabola is concave down. Finding the axis of symmetry and the vertex of the parabola. So the axis of symmetry, we have an equation to find the axis of symmetry. That is the x value of the axis of symmetry is negative b over 2a. And then as you can see here on this graphic, our axis of symmetry is a vertical line. We can represent that as a dotted line, or we can just think about it as a vertical line that goes through the vertex of the parabola. And our vertex falls at the x point of the axis of symmetry. So to figure out what the value of your vertex is, you plug in your axis of symmetry value, and that gives you your y value. So your vertex is an ordered pair of x, y. That x is your axis of symmetry. Y is the output when your axis of symmetry is your input. So for example, we're going to find the axis of symmetry and the vertex for negative 3x squared plus 6x plus 1. So again, our formula for axis of symmetry, or a of s, is negative b over 2 times a. In our case, we've got negative 6 over 2 times negative 3, which is equal to negative 6 over negative 6, which is positive 1. So your axis of symmetry is x is equal to 1. Now to figure out your vertex, you need to find f of 1, which is negative 3 times 1 squared plus 6 times 1 plus 1. So negative 3 times 1 plus 6 plus 1, negative 3 plus 6 plus 1, 4. So we have a vertex here of 1, and again, that's your axis of symmetry value, 4. And that's the ordered pair. So that's how you find your axis of symmetry and a vertex for a function in standard form. Now, roots, zeros, and x-intercepts of a quadratic, it's where y is equal to 0 in your quadratic, and we have to remember that all three of these have the exact same meaning. So roots, zeros, and x-intercepts, they're interchangeable in how we refer to them. You're going to see different problems asked for the roots, you're going to see different problems asked for the zeros, different problems asked for the x-intercepts. All three mean the same thing. It means where your function is crossing the x-axis and where y is equal to 0. For quadratics, you can find this through factoring. I would say most quadratics in your textbook can be solved through factoring. However, most quadratics in the real world aren't solved through factoring, and we would use the quadratic equation in order to figure out what our x-intercepts are, or the quadratic formula. All right, the x-intercept of a quadratic function. So first we have to remember that the quadratic equation is negative b plus or minus the square root of 4 of b squared minus 4ac all over 2a. So that's your quadratic equation. And then we have some rules for the x-intercepts of a quadratic function, and that covers the discriminant. And the discriminant is this value under the radical. So we call the b squared minus 4ac the discriminant. If the discriminant b squared minus 4ac is greater than 0, the graph of f of x is equal to ax squared plus bx plus c has two distinct x-intercepts. Again, if it's greater than 0, that means we can take the square root of this function, and since we have plus or minus, that means we've got a positive and a negative square root, or we're adding that square root and we're subtracting that square root from negative b, so that's two intercepts. If that discriminant, if b squared minus 4ac is equal to 0, that means the square root of 0 is 0. You only have one x-intercept, and in this case, it's also going to be the vertex. So if you only have one x-intercept for a quadratic, that x-intercept also is the vertex. If we think about that axis of symmetry and how every point is going to have a mirror image except for that vertex value, that makes sense. And then finally, if the discriminant b squared minus 4ac is less than 0, there are no x-intercepts. If we have b squared minus 4ac less than 0, that means you have a negative number. That means if we took the square root, we would get an imaginary number, and we are not, if we have an imaginary number, that means we don't have any x-intercept. We can't get real numbers. So thinking about the discriminant, thinking about that value under the square root in the quadratic formula gives us a good idea of how many x-intercepts we can have, if we can have any at all. We'll never have more than two. Quadratics have at most two x-intercepts. All right, so find x-intercepts example. So find the x-intercepts of the function negative 3x squared plus 6x plus 1. So I go through here. I'm going to first try factoring. So I've got an a times c of negative 3. So I want numbers that multiply to make negative 3, but then add to positive 6. And I am not thinking of anything off the top of my head that multiplies to negative 3, but then adds to positive 6. So I'm going to go ahead and plug this in to my quadratic formula. So I've got negative 6 plus or minus the square root of 6 squared minus 4 times negative 3 times 1 all over 2 times negative 3. So now I have negative 6 plus or minus the square root of 36 plus 12 all over negative 6. Negative 6 plus or minus the square root of 48 over negative 6. I'll do a prime factorization of 48. I can take 4 out, so I get negative 6 plus or minus 4 times the square root of 3 all over negative 6. So that means my x-intercepts are going to fall at two places, negative 6 minus 4 times the square root of 3 over negative 6, and negative 6 plus 4 times the square root of 3 all over negative 6. And I should point out, actually, these are what these x-intercepts would look like: negative 6 minus 4 times the square root of 3 over negative 6, and negative 6 plus 4 times the square root of 3 over negative 6, and then 0. Because my y value is 0, these are both x-intercepts. So go ahead and plug these values in on your calculator. I'm going to do so now. Negative 6 minus 4 times the square root of 3 divided by negative 6, and I get one x-intercept of about 2.150, and then I get another one, negative 6 plus 4 times the square root of 3, and then negative 0.150. All right, so now graphing using the x-intercepts and the vertex. So once you have your x-intercepts and your vertex, what you would do is you would say to yourself, okay, I know my vertex for this function. This is the same function we have been using. We already know that our vertex here is 1, 4. We know that our x-intercepts are at 2.150 and negative 0.150. I'll go ahead, I'll place a point at 1, 4. I will place a point at roughly 2.15 and a point at roughly negative 1.5 or 0.15. And then I will draw my parabola shape through those points, and there you go, you've graphed your quadratic. So once you have your vertex and your two x-intercepts, that's more than enough to graph a quadratic. I could represent the fact that I've got an axis of symmetry. This is in no way, shape, or form required, but this can be used for a good check. So I look at my x-intercepts and where they're at. My x-intercepts do line up with that axis of symmetry. They are both 1.15 x values away from the x value of my vertex, which means that they are equidistant from that axis of symmetry, which is very important for my x-intercepts here. So that looks good to me. So I've got a pretty solid graph here. I did a quick mental check, and I even drew my axis of symmetry just to make sure it lined up fairly well. All right, let's say that we were going to graph without x-intercepts. So here, the first thing we would do is find our vertex. So I need my axis of symmetry, which is going to be at negative 1 over 2 times 2, which is equal to negative 1/4. I need my vertex value, so I need f of negative 1/4. So this is 2 times negative 1/4 squared plus negative 1/4 plus 1. So this is 2 times 1/16 minus 1/4 plus 1, 1/8 minus 1/4 plus 1, 1/8 minus 2/8 plus 8/8. So this becomes 7/8. So now I have a vertex of negative 1/4, 7/8. Now that I've got that vertex value, I'm going to think about factoring. My a times c here is positive 2, so I would need a number that multiplied to 2, but then to positive 2, but then added to positive 1. That doesn't exist, so I'm now going to think about it in terms of my quadratic formula. So negative 1 plus or minus the square root of 1 squared minus 4 times 2 times 1 all over 2 times 1. Well, when I look at this, I end up with negative 1 plus or minus the square root of 1 minus 8 all over 2 times 1. I know that 1 minus 8 is negative 7, so I can't get a square root here. So now I know that I'm not going to get any x-intercept. And this makes sense because if my vertex, and we're actually going to make this easier, we're going to count my y's by 1/8. And we're going to count our x's by 1/8 as well. So that means my vertex would fall at this point here. This would be the point negative 1/4, 7/8. Okay, so what do? Well, this is where I'm going to use my axis of symmetry. I know that I've got points that are mirrored across my axis of symmetry, and I've got a vertex here. What I can do is I can use my y-intercept. All of these will have a y-intercept. They might not have x-intercepts, but they're all going to have something where y is equal to 0. So f of 0 is equal to 2 times 0 squared plus 0 plus 1. So f of 0 is equal to 1. Another way to remember this is your y-intercept is always c. So your y-intercept is always your c value. So in this case, I'm counting by 1/8, so that means my y-intercept is going to be over there. And then since I went up 1 and over 2, I'm going to go up 1 over 2 here. I'm going to mirror and make my axis of symmetry and then go from there. Now let's say that you're at a point very far from your y-intercept. Let's say that you've got a vertex value where x is equal to 15 or something. Well, if your vertex value is x is equal to 15, go ahead, draw your axis of symmetry through 15, and then plug in 14 or 16, and then still use that mirrored point. Only reason I'm using my y-intercept is because I'm very close to my y-intercept right now. Negative 1/4 is very close to 0. If I have an x value which is crazy far away, I'm going to choose a different point to use with my axis of symmetry. It's just like when we did those transformations when I changed my origin and I went through and then I plugged in numbers. I'm going to plug in numbers close to my vertex, and I'm going to use the axis of symmetry to go through and graph the quadratic. And that's if I don't have my x-intercepts. All right, vertex form of a quadratic. The vertex form of a quadratic function is as follows: a times x minus h squared plus k, where h, k is the vertex and a is the stretch factor. So we've already done this a little bit. We looked at this in terms of transformations. But now we actually want to use vertex form for other things. Vertex form is great for graphing because you're just right away you're given the vertex, and you can use this as a parent function idea in order to graph. You're given the vertex, you don't have to solve for your axis of symmetry, you don't have to plug it back in. But it's also good for finding information of finding a quadratic if all we have is a couple points. So determine the quadratic function whose vertex is 1, -5, and whose y-intercept is -3. So this means we've got 2 points. We've got a vertex of 1, -5, and we've got a y-intercept of 0, -3. Vertex form is y is equal to a times x minus h plus k, where hk is your vertex. So in order to solve this first, I'm going to write out y is equal to a times x minus 1 minus 5. I've plugged in my vertex value, my hk of my vertex value, into that vertex form. Now that I'm here, I don't, and this is all squared, sorry. So that's squared. Now that I'm here, this is not the quadratic function that I'm looking at. This is not the correct quadratic function because all I have is a. That a value can be anything. This is a great representation of every quadratic function that has a vertex at 1, -5, but that doesn't include the stretch factor. I need to solve for the stretch factor. Well, how do I do this? Oh, well, I've got an xy value here, and I've got another point right here. So I'm going to go ahead and I'm going to plug in -3 is equal to a times 0 minus 1 squared minus 5. I just plug in the xy value of the one point I know that is within this quadratic function, and that will allow me to solve for a. -3 is equal to a times -1 squared minus 5. -3 is equal to -a minus 5. -a is equal to +2. A is equal to -2. So now I know the general form of this equation is y is equal to -2 times x minus 1 squared minus 5. I'm going to do a quick check of myself to see if this makes sense. I've got a vertex at 1, -5, and then I've got a y-intercept at -3. So something's gone wrong here because I should have a concave up parabola. If my vertex is at 1, -5, and my y-intercept's at -3, that means it should look like this. So I should have a positive a value here. So I've made a mistake in my math somewhere, and I realize I made the common mistake of when I squared my negative, I kept it negative. This should be positive. So positive a minus 5 is equal to -3, which means that positive a is equal to +2, and this makes much more sense. So this should not be a -2, this should be a +2. So you can do a quick check of your math that way too. I can see that I've got that negative a value. That means it should be concave down, but the points that I had led to it being concave up. So now I can say for certain this actually should have an a value of +2. Now that I've done this, I don't have this written in the example here, but I promise you every quiz and test that I have this, I'm going to write it in standard form. To write this in standard form, you just expand it. So 2 times x minus 1 times x minus 1. Remember, when we square binomials like that, that means we are multiplying it all by itself and requires distribution. So y is equal to 2 times x squared minus 2x plus 1 minus 5. Y is equal to 2x squared minus 4x plus 2 minus 5. And then y is equal to 2x squared minus 4x minus 3. I can do some quick mental checks for myself here to see if this matches up. All right, well, I've already told you your y-intercept is always just your c value. My c value here is -3. My y-intercept up there is -3. Perfect. So my y-intercept and my c value match up. Let's think about our axis of symmetry. Axis of symmetry is -b over 2a. So in our case, it would be -4 over 2 times 2, which would end up being +1. So that means our vertex axis of symmetry here is +1, and then we could even plug this in. 2 times 1 squared minus 4 times 1 minus 3, so that's going to be 2 minus 4 minus 3, that's going to be -2 minus 3, that's -5. So you have a vertex at 1, -5. I just did a bunch of quick mental math there. You can write that all out, and I can say to myself, all right, this is a standard form of a quadratic that matches up with a vertex at 1, -5 and a y-intercept at -3. And I have a note here. I guarantee that you will see this question on at least 4 tests and quizzes. At least. I ask this question frequently. This is just something where it's like you either know this or you don't. This is not too complicated. It's knowing where to plug in things and how to plug them in. It's very similar to solving for b on a linear equation. Solving for your y-intercept on a linear equation given a slope and a point. Same concept here. And I trust that you should be able to do this, so you will see this pretty frequently. Maximums and minimums of a quadratic. If your a value is negative and the graph is concave down, we refer to this vertex value as a max. It's the peak. And then if you have a concave up parabola, this vertex value will be your minimum. And this is just kind of a mixture of things that we've already learned, plus adding in the vertex value. So again, here we're going from increasing to decreasing, that's a maximum, decreasing to increasing, that's a minimum. All right, so determine whether the quadratic function x squared minus 4x minus 5 has a maximum or minimum and find the value. Well, right away, I can tell you that this is going to be a minimum. My a value is positive. And since my a value is positive, that means it's concave up, which means I've got a minimum. Find the value. This means I actually have to go through my axis of symmetry here. Is -b over 2a. So that's 4 over 2. My axis of symmetry is 2. So I've got x is equal to 2. I need f of 2, which is going to be equal to 2 squared minus 4 times 2 minus 5. So that's 4 minus 8 minus 5, -4 minus 5, -9. And so I've got a vertex minimum at 2, -9. So if it asks you to find the value of your max or min, that just means find your vertex. All right, you have a homework assignment tonight. Covers pretty much everything with quadratics. If you have any questions or concerns, please reach out and have a great night.